Hi, thanks for coming by. This paper is about automatically detecting the sound of people laughing in an audio file. The output of a laughter detection system is just a set of time windows indicating where laughter happens. So why should we be interested in accurately recognizing laughter? Well, one main reason is that it's a strong signal for understanding emotions in a variety of different situations. And this project actually began for us with a HCI study in 2018, where we explored what it was like for people to try to capture and preserve moments where they laughed during their daily lives. And in the process, we implemented a state-of-the-art machine learning model for laughter detection, but we found that it gave us a lot of false positives, especially when participants came back with audio recorded on their smartphones in noisy environments. And this sort of makes sense because people rarely laugh by themselves in a quiet room. Now, we realized after this that laughter detection had really only been evaluated thoroughly in controlled recording environments, so we didn't know how to quantify how well it would actually work when you take it into the real world. And one of the main contributions of this paper is a new set of annotations that allow us to evaluate laughter detection in real-world environments. We used AudioSet, a large collection of 10-second YouTube clips that have been tagged with about 500 different sound categories, including laughter. And the problem with AudioSet is that these tags only indicate that a category occurs somewhere in that 10-second window, but they don't say where. So we had an annotator listen to 1,000 of these clips and segment out all the regions containing laughter much more precisely in a similar format to what you can find in speech datasets. Now, given this evaluation dataset that's a bit more realistic, we tried to answer some questions about how well laughter detection works in the real world and what are the best ways to train models. So there's two different options for training data. We can use the switchboard data that we'd used in the past, which has good labels but is only recorded in one environment. Or we can use the rest of the 10-second clips from AudioSet, other than the ones we segmented out for our test data, which are in domain, but in this case our training labels will be noisy because we don't know where exactly the frames are that the laughter takes place in. And so we also tried a few different modeling setups varying the architecture and augmentations and so on. And so the numbers on the right here show performance in the real-world environment. We can see there's a steep drop-off in performance compared to when you evaluate the same models using the switchboard test data. But if we use a ResNet architecture and add some data augmentation, the drop-off is a little bit less steep. And we also experimented with what happens training on the unsegmented AudioSet data with noisy labels, and it does turn out that the label noise is really a problem, so it's still better to train on the segmented data from switchboard. So of course there's still a lot of room for improvement, and we hope that the community will continue to work on this problem using the segmented data that we've annotated in this paper. So thanks, and you can access our code and data and train models at our GitHub page.